talking about keto-enol tautomerism. Now, what is keto-enol tautomerism? It is an isomerism that exists between ketone and an enol. An enol is a structure which has an ene and an ol. Ene is basically a double bond, and ol is an hydroxy group. So both put together, it's going to be the enol. Okay, and tautomer is a special word for isomers. And for most ketones, keto tautomer is the isomer which is going to be more stable and in about 99.9%. But the enol form is going to be less stable, which is going to exist in about 0.1%. Okay, but there are a few exceptions. The first exception that we are going to see is the beta diketone. Here, the fraction of the enol tautomer in solution is considerably greater for beta diketone. So here is the beta diketone, which is the keto tautomer, and here is the enol tautomer. And as you can see, the enol tautomer has an ene, which is a double bond, and an hydroxy group, which is the OH group. And this structure is actually stabilized in two different ways. The first one is the intramolecular hydrogen bonding. There is an hydrogen bonding that exists between the hydroxy group and the oxygen. And then the two double bonds that are present in here are actually conjugated. So these two factors are going to bring in this extra stability to the enol structure. Okay, and the next exception that we are going to see is phenol. Now, phenol is generally stable in the enol as an enol conformer. As an enol tautomer. Okay, enol tautomer is more stable because it has the aromatic structure in it. So this part of the molecule is actually benzene, and we know that the benzene is a stable molecule because of its aromaticity. And that's the reason why the enol tautomer is more stable, whereas the keto tautomer doesn't have any aromaticity in the molecule, because of which it is comparatively less stable. And keto-enol tautomerism can be catalyzed either by base or by acid. We'll look into the mechanism of both the scenarios. Okay, so let's look into the base-catalyzed reaction. For the base-catalyzed reaction, let's take an hydroxide ion. The hydroxide ion is first going to go abstract this hydrogen, and it's going to thrust these electrons onto carbon to form the enolate structure. So this is your enolate, and we know that the enolate is going to have another resonance structure by pushing in these electrons in here and thrusting these electrons onto the oxygen. Okay, so this is the second resonance structure of enolate. And once that oxygen gains its negative charge, it's going to go abstract the hydrogen from the water molecule. So here is the water molecule, and it forms the enol structure. Okay, so this is the basic mechanism for the keto-enol tautomerism, and it's super straightforward. Now let's go on to the acid-catalyzed keto-enol tautomerism. For the acid-catalyzed keto-enol tautomerism, the first step is the acid protonates the carbonyl oxygen. So here is your carbonyl oxygen. So that's going to be protonated in the presence of an acid. Okay, so it's going to go grab this hydrogen, okay, and thrust these electrons onto the oxygen to form water molecule. And that water molecule is going to go abstract this hydrogen. Okay, and those electrons will be pushed on here. And because there is a double bond right there, that's going to break, and the oxygen will be neutralized. The positive charge on the oxygen will be neutralized. So that's going to be the structure of your enol. So this is the basic mechanism for the acid-catalyzed and the base-catalyzed keto-enol tautomerism. And the next thing is, I want you guys to definitely draw the structure of keto and enol tautomers. So probably there might be some questions in the exam.